from the homework, page 555, number 29. I'm not going to write that whole thing out because that's ridiculous. I will say it though. It says the Mesopotamian civilization was dated by using carbon-14 dating. And immediately I'm thinking, okay, carbon-14 and the section that we're in, we are in the realm of exponential decay. So before I do anything, I'm just going to go ahead and have this written down somewhere on my paper. Because of course, this whole chapter has been about this one function. And as soon as I hear carbon-14, I'm thinking, okay, we're going to have something with exponential decay. This is going to help me out somehow. So, okay. A piece of wood discovered in an archaeological dig was found to have lost 62% of its carbon-14. Determine the age. Okay, so first off, I'm not exactly sure what to do here. So what I'm going to do when pretty much with all the questions I ever do, but especially with the ones where I'm just like, I'm not 100% sure what to do. I'm going to start with a graph. And the graph, of course, like I'm taking a cue from this section. Like I know what this section's about. Everything, I've already said it and written it up here. It's something like this. And now since we're talking about some sample, a piece of wood, do you know how carbon-14, since we are kind of playing free and loose today, do you know what carbon-14 dating is? Do you know how that works?
I have a sort of the very limited idea of what it is.
Let me give you an idea. So you have a living creature. This living creature, say it looks like this. There's your living creature. And we are carbon-based beings.
Yeah.
Carbon is the backbone of every structure in your body.
Yes.
Okay, right? It is everywhere. And so another thing about living beings is we exchange the stuff. Like the atoms that you have in your body right now are not going to be the atoms you have in your body in 7 years. The estimate is about every 7 years, these things get completely replaced. But it's not like an all-in-one go. It's not like your body waits 7 years and goes, oh, and then like dishes out, like, just gets rid of all these atoms. It's constantly happening that you have an exchange between your surroundings, the surrounding universe, and what's going on in your body with carbon. Some proportion of the carbon that's in the universe, or we'll just say on planet Earth, is a special kind of carbon, which is carbon-14. Mm-hmm. Now, what do you know about chemistry? You know about, what's the nucleus of an atom?
The protons and the neutrons. Like
protons and neutrons, okay. Carbon has how many protons? Do you know?
Oh, isn't it 19? 9, 8, 4, 2, 6.
Keep throwing them out there. We'll hit it. It's 6. It has 6 protons. And the protons being positively charged give the atom its character. That's basically, an atom is determined by the number of protons that it has. Because protons are positively charged, they attract a certain number of electrons. And well, if there's 6 protons, it attracts 6 electrons. And then because of that interaction between the positive and negative charges and stuff like that, it creates a certain shape and size of an atom. And that shape determines how it reacts in the world. But it's completely determined by the number of protons, okay? Because the protons, again, determine the electrons, which is kind of the outer, the part of the atom that we see, if you will, or the part of the atom that interacts with the world is by its electrons. And so since the protons determine the number of electrons, then the entire character of the atom is determined by the number of protons that are in it. Any atom with 6 protons is carbon. I don't care if it has no neutrons, if it has 5 neutrons, if it has 1 billion neutrons. Well, 1 billion is probably on pushing the limit. But even if it has 1,000 neutrons, it's not going to change its character because, oh, buddy, okay. It's not going to change the character of the atom because, I'll say it one more time, the character of the atom is determined by the number of protons that it has. Here you go, buddy. And so there are a bunch of, so these atoms, these nuclei, right? You already said it, in a nucleus, it has protons and neutrons. Neutrons kind of help glue the protons together. Because in case you hadn't noticed, positive charges push each other apart. And you can't just grab a bunch of positive charges and hold them together. The neutrons are what holds it together. And like I said, for carbon to be carbon, it has to have 6 protons, but the number of neutrons is variable. Some of them have 6 neutrons, so that would be 6 protons, 6 neutrons together give you what we call carbon 12, because there are 12 things in the nucleus. Some of them have 6 protons and 7 neutrons, which gives you carbon 13, which is a total of 13 things in the nucleus. Finally, 6 protons and 8 neutrons gives you something called carbon 14. The thing is, though, carbon 14 is not stable. It doesn't stay as carbon 14. Because again, like I was fibbing when I said you could have 1,000 neutrons in the nucleus. That ain't gonna happen. Maybe for like a fraction of a second, you could make something like that happen. But there are certain numbers of protons and neutrons in here are more stable than others. And over time, things like to revert to the most stable configuration. And so carbon 14 will lose 2 neutrons over time. And when that happens, it drops down to 6 protons, 6 neutrons, drops down to carbon 12. Or it might be that it goes through 13 first and then goes to 12. What? Who cares? This isn't a chemistry class, but this is important stuff. You do need to know this, whether or not we're talking about math or not. Like, this is really important stuff to know. So the way that this works, okay, is there is a certain proportion of carbon 14 in the universe or on the planet Earth. And I'm not sure exactly what it is, but you could think about it like, okay, there's a bunch of carbon 12 floating around. And for every, let's say, 4 carbon 12s, we have 1 carbon 14. So that would be 80% carbon 12, in this case, 20% carbon 14. And so if you take a sample of something that's alive right now, like we go and find a tree and we take it and burn it up and just look at the carbon, and we say, okay, what's the proportion of carbon, of all the carbon, how much of it is carbon 12, how much of it is carbon 14? And we see that, okay, there's 20% carbon 12, sorry, 20% carbon 14, 80% carbon 12, then it has the same proportion as the rest of the world. And we'd say, this thing must have just died. You must have just chopped this tree down. We say that. Well, this is what happens. And this is what this is all about. Is that this cat, or whatever it is, now it's a cat. This cat is alive. And so it is constantly changing its atoms in exchange with the atoms in the rest, the larger world, in the atmosphere, through the foods that it eats. That is a cat, that's right. Through the food that it eats and stuff like that. And so while it's living, it has the same proportion of these atoms in it. So if this cat were to die today, and we analyzed, okay, how much carbon 14 does it have? How much carbon 12 does it have? We'd see, okay, it's about an 80-20 balance. But then this is where it gets cool, is that let's say the cat dies. the cat dies and it no longer is exchanging its atoms with the outside world. Well, then it dies with this proportion of carbon-12 in its system. 80% of it is carbon-12. 20% of it is carbon-14. But then as time goes on, this decay process is always happening. And so a carbon-14 decays and turns into carbon-12. But now there's no exchange. That was already going on while the cat was alive. But there's no exchange. So it's not getting that new proportion of 80-20 carbon-12. And so now it's starting to accumulate carbon-14 or carbon-12. And so as time goes on, eventually we have, like, say, 90% of it is carbon-12 and only 10% of it is carbon-14. So we have a dead cat. There's our dead cat. We find some remains of a dead cat and we say, okay, how long has it been dead? And so we're going to take part of its body or whatever, burn it up, and just analyze the carbon. And we get it and we see, oh, of all this carbon, 90% of it is carbon-12 and only 10% of it is carbon-14. So we could say then, okay, this cat then started off with a certain amount of carbon-14. We know because we expect this cat to have 20% carbon-14 when it dies. But now that has decayed to 10% of the total, which, and this isn't part of the work right now, but to, like, I guess if it started with, let's say, and this is a ridiculously small number, but let's say it started with 1 million atoms of carbon-14. Then after some amount of time, now it only has 500,000 atoms of carbon-14. So that's kind of what's happened. And we want to know, how long did that process take for a million atoms of carbon-14 to turn into 500,000 atoms of carbon-14? And so that is what this is about. The way and the reason that we can do this type of thing and figure out how long this cat's been dead is because carbon-14 decays at a regular rate. It always takes the same amount of time for half of the carbon-14 to go away. And so, okay, let's do that first. Let's figure out what that is. And so, no, you don't need any more of those. You've had way too many of those. So this is what's going on with decay. You've seen this before, but we're going to say, okay, the living thing died and had a certain number of atoms of carbon-14. And so that's what I'm saying right there is that quantity. That's the initial quantity of carbon-14 in animal. And we'll say that's at the moment that it dies, right? Because as long as it's alive, it's exchanging carbon, and you're going to have that nice 80-20 proportion or whatever it is. And then that proportion, you could find, okay, that's how many atoms you should have in that proportion. That's how many atoms, that's the initial quantity of that. Or maybe we measure it in grams or whatever, it doesn't matter. And so this thing decays exponentially, and it takes a certain amount of time for that quantity to reach 1/2 of the original quantity. So that amount of time that it takes is called what?
The half-life?
The half-life. There you go. And I'm just going to write it as H. That's the half-life. So in other words, if I take that number H and plug it in right here, I'll get 1/2 of the original amount. That's what that is. And for carbon-14, it says in problem 28, the one just before that, it says that the half-life of carbon-14 is 5730 years. So again, it says that if I plug this in, if I plug in H, the half-life, into here, then the amount that I get is 1/2 of the original. So this nifty little picture means it doesn't matter where you are in the universe, it's going to take that long for this process to happen. And so now, okay, so we've covered that, but now I want to go back and do this the way that I originally wanted to do it, which is to think about the problem. So I'm going to erase our cat. I'm sorry. I'm going to get rid of all this stuff here. So does that make sense? What carbon-14 dating is? I
think so. Yeah.
Okay. And this isn't for our class. This is just for your own edification because everybody should know this. Okay, you could have some of these. Here you go, buddy. All right.
It sounds a little bit familiar. We might have gone over it in chemistry, but I don't quite remember.
Yeah. And so that's the idea. Just while there's a constant exchange of atoms going on, you're going to have the same proportion as the rest of Earth. Mm-hmm. And once you die, you stop exchanging. And so then the carbon-14 that you still have starts to decay. And so then we see the proportions when something dies and says, oh, that's off. And so then we could say, well, how much is it off? Well, it decayed by about however much it's decayed. So we could find a time. And that's what we're trying to do with this question right now. Because it takes a constant amount of time to lose half of your initial amount, which is that long. Okay, so this is kind of background info. But now what I want to do is draw a picture of the thing that's happening now. And so to remind ourselves, it says that civilization was dated by using carbon-14 dating. Okay, so we're going to do something with exponential decay. A piece of wood discovered in an archaeological dig. This piece of wood was alive at some time. It is not alive anymore, and we want to know how long has it been dead. That's the idea. If we could find out how long, when did this thing die? How long ago was it that this thing died? Then we could have an idea of, well, they must have chopped down the tree around this time. And so we could date the civilization. Okay, so it was found to have lost 62% of its carbon-14. Okay, so let's think about it this way. And again, I'm kind of going back to not sure what to do, so maybe I should draw a picture. So we're going to say, okay, the piece of wood then started off with a certain amount of carbon-14. That's what I'm going to call that right there. I'm going to say this is we'll just say grams, the number of grams of carbon-14 in log when dead. And dead is when time equals 0. So it died at time 0. Okay, this is exponential decay. And so it decays by some amount and does something like that for some amount of time. And now what it says to do is determine its age. So in other words, we're trying to find the amount of time it took for the initial amount to decrease to some new amount. Well, what's that new amount? And this is what I was saying when you asked me for help, right? And so this is how I'm going to think about it. This says, I'm going to write it up here so we could really look at it. It was found to have lost. It lost 62% of its carbon-14. Now we need to translate that into this picture right here. And the carbon-14 that it's referring to is this initial amount of carbon-14. That's what the context of carbon-14 dating means. That they say it lost 62% of its carbon-14. That means that it had its maximum amount of carbon-14 in it when it died. And whatever amount that is, what's left, it lost 62% of it. So let's do this. Let's just say I have some stuff. And let's say I have 100 grams of stuff. And I told you that we lost 80% of this stuff. How much stuff would I have left? So I have 100 things, and then I lost 80% of those things. How many things do I have left?
20.
You should have 20. Why? And this is how I visualize it. I think, well, if that's the whole right there, and if I lost 80% of it, that's 80% of the whole. And then just like you're saying, okay, 20% would be what you have left. And so if I had 100 things and I lost 80% of them, I would have 20 things left. Okay, let's generalize this a little bit. Let's suppose that instead of 100 things, let's say I had 5 grams of stuff. If I lost, and I don't want an actual round number, don't pull out a calculator or anything. But let's think about this. If you had 5 grams and you wanted to find, because you already told me that the percentage of it that we have left was what? If I lost 80%, I would have what percent left over?
20%?
You would have 20% left over. So how do we take 20% of 5? It's a doggy. That's right.
Thank you. Sorry. Sorry.
That's okay.
20% of 5.
Uh-huh.
You just, oh gosh. You
multiply something by something.
multiply 5 by 0.2.
There you go. Exactly. Exactly. You take whatever your initial amount is and you multiply it by the percentage, right? That's how you take a percent. And just to make sure here, let's look at what we did. When it was 100 grams, we said it would drop down to 20 grams. And let's see if that makes sense. 100 times 0.2 is the same as, well, the point means move this over 1 decimal place. And then 20, yeah, that's exactly what it means, right? Please don't touch my stuff. So, okay, now here's the hard part. Well, there's kind of 2 hard parts here. It says it lost 62% of its initial value, of its initial amount. And so what's my amount that's left over? If I lost 62%, what percent do I have left?
You lost 62%?
If I lost 62, what would I have left?
Hold on. 38%?
Yes, I was thinking about this earlier and I kept saying 48. Obviously, 48, right? Yeah, and so 38% would be left over. Okay, now we're almost done here because as you can see, we're closing in on this number right here.
Okay.
Okay, so if I started with 5 grams of carbon-14 and I have remaining 38% of that 5 grams, I would do what times what if it were 5 grams?
You would multiply, I think, 0.38 times 5.
0.38 times your initial amount. That's right. And that's how you would find out how many grams you have left, in the same way we did over here with the 0.2% and stuff like that. I mean, sorry, 0.2. Here we're going to say, okay, if you took your initial amount, whatever it happens to be, and multiply it by 0.38, then we'll have that new amount. And don't lose sight of what we've done right here. This is what's one of the things I love about these types of questions is I'm always thinking, don't I have to know how much you start off with? Like, don't you have to tell me like you had 55 million grams, or that would be a lot, 5,500 grams of carbon, like in this cat or piece of log, right? Well, no, and you should remember why here in just a second, why we don't need that. But this is how we're going to deal with that. Right now, I just translated the situation they gave me into a picture. And here I'm going to say the time that this happens, it's a special time because that's what they're asking me, right? Determine its age. That's the age that we're talking about. I'm going to give it a special name. I'm going to call it big capital T right there. Capital T is the time that it took for the full amount of carbon-14 to decay to 38% of its original value right there. So is this picture making sense?
Yeah.
Okay, so now here's the question is, okay, we need to find this. And right now I'm going to take this whole context of everything that we've done and just forget about it. Right now, I'm just going to look at this picture right here and think, okay, we're trying to find T. That's an input variable. So that's the value I'm trying to find. And so I'm looking at this equation right here because I know that this thing is given by this right here. Pt equals P0 e to the kt. And I'm thinking, okay, here's what do I have? Well, I have an output value. Okay. Looking over here, and again, right, this is very much like looking at y equals mx plus b. You know that the input and the outputs are not going to change. Those are, I mean, those are the things that you're working with, right? And so then it comes down to two numbers that we need to find in order to answer any question about this line. Same thing is true here. Our inputs are t, our outputs are this nifty symbol p of t, which is just y. But then it comes down to finding two numbers to be able to answer any question. We need to find P0 and we need to find K. But in this case, right, and in cases like this, we're not going to need to actually find P0 because we've done this before, right? I know that if I plug in a value and I get this as an output, then that being my output, I'll be able to divide both sides by whatever P0 is. And so it's like with this setup right here, with these outputs, I probably spelled that wrong, but P0 is superfluous. We don't need it. It's unnecessary in order to solve our equation. And so that's kind of nice, but I'm tucking that away in the back of my head here. And I'm going to think, okay, so we have an equation. I'm trying to find an input. I have an output. So that part's done. P0 and K. So those are the last two things I'm going to need. But I just noticed that P0 is not going to matter, actually, because the output includes P0. Okay, and so it's superfluous. We don't need the P0 to actually find it. Then the only thing we need, and we actually do need it, we need K. That's the only bit that I need in order to solve this problem. And so here we go. How do we find K? Well, that's the cool thing about exponential decay. Like I said, it always, always, always takes this amount of time for carbon 14 to decay to 1/2 of its original value. Since that's the case, we have an input. We have outputs that help us cancel P0. We will be able to solve for K. So that's the idea. We're going to use our exponential equation, plug this stuff in order to get K by itself. So first, I'm just going to write it as P of T equals P0, e to the KT. Now let's plug in that H. And you tell me what to write here. What should I get if I take this function and plug in a 5730 for T?
I'm gonna write it out.
Yeah. Oh. Don't solve it. Just tell me what the first thing we need to write there when I plug that thing in is.
$57.30. Well, wait, the first thing, as in like write out P0 to the K times.
Yeah. So what I'm saying here is, so this is an input-output relationship.
Oh yeah.
Right? And that's how we always want to think about everything, really. That's gonna make your life so much easier. So, okay, what's the input?
$5,730.
There you go. Where does it go?
The T.
Yeah, and I'm gonna plug it in here on the right-hand side for T. So
Yeah.
P0 e to the unknown K, the thing that we're trying to get by itself, times 5730 equals what?
E times 5730 PT.
Well,
Oh no, 1/2, right?
Well, let's see. P of 5730. It's true that, yeah, P of 5730 does equal this. But this represents something else on this picture. What is that? A function is a relationship between what's and what's.
Inputs and outputs.
Mm-hmm.
So 1/2.
Well, not exactly 1/2. 1/2 of whatever the original value was. Right? So 1/2 times P0. And right here, like this is one of the reasons I drew it. And this is one of the reasons I draw everything, is the little bit of work to draw stuff out takes all the guesswork out of this. Because I could see by the drawing that I've done is that when the input is 5730, then the output is 1/2 times P0. And so.
Oh. Okay.
Right. And so this is the output. That thing, P of 5730, represents the output of this function, which tells me that when the input is 5730, the output is 1/2 P0. And so I'm going to replace the output symbol with 1/2 P0 equals P0 e to the K times 5730. And this is what I was saying earlier with the P0 being superfluous for these types of problems. Not always, but in this case, it is, because it shows up on both sides of the equation. multiplicatively, right? Like it's multiplied by. And so we could say, oh, well, why don't we just divide both sides by P0? And so that's what we do. Dividing both sides by P0 gives me 1/2 equals e to the k times 5730. Why am I doing k? What am I doing here? Oh, that's right. I need k. That's all of this right here is just to find what number k I need to plug into my scenario that I care about, which is this log that has decayed down to 38% of its initial value. Okay, so we're almost there. Let's get k. How do we solve this equation for k?
Take the log,
Which log?
common log. Or no, the natural.
Natural log. Right, natural log.
Natural.
Yeah, L and natural log of 1/2. And I'm not going to do that because the natural log of E pulls out whatever it is. So I'm just going to say, okay, K times 5730, which means K equals what?
L, the natural log of 1/2 over 5730.
There you go. Okay, there we go.
We have a minute left, just so you know.
Oh, thank you. So all of that was to get down to that point right there, right? All of this talking about half-life and blah, 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 was simply to get that K. Because now, and I'm gonna jump off here in a minute and get back on, but because now, as we said, right, normally we have to find K, we have to find P0, we have to find M and B in a line. But in this case, this is going to be one of those nifty cases where the actual initial amount won't matter because it's going to show up on both sides of an equation right here. And it will end up canceling out. And so that's just one of the things that you have to know as you go into this, like as you're trying to eliminate the things that you need and find all your unknowns. Something to know is going to happen a lot, and that's really nifty. And so now we're just trying to find K, which we just found. So let's plug along. All right, so we got to here, right? We got to K. You have K written down because I'm going to get rid of all this stuff.
Yep.
Okay. So we found K. Comes from the fact that K is always the same for carbon-14. And so let's go ahead and rewrite this thing and say, we found K. So I'm going to rewrite this whole thing as e to the kt, or in other words, e to this natural log of 1/2 divided by 5730 times t, just like that. I'm going to use parentheses. Okay. Now there's only one thing we need to know, and that is t. And just as we did before, I'm going to start with my function, p of t equals P0 e to the natural log 1/2 over 5730 times little t. Now, this says that when I plug in a big T, I get out what? And so, in other words, what I'm trying to figure out, how can I rewrite this thing with this information now so that I could get the variable that I'm trying to find? So you tell me, what do I need to write up here?
All right. 1 second. I'm gonna write it down. T equals P0. Oh, I have a question.
Yes.
So I'm wondering if I did my homework incorrectly because I didn't write, I solved for a K so that I had a decimal instead of a complicated fraction like that. Is that?
I asked you not to do that, but
okay. I
like most people won't. However, so I'm going to say one thing. If I ask you to write, like if I say I want exact answers, and anytime a teacher of any sort says they want an exact answer, they're looking for something like this.
Yeah.
Often, I know, and oftentimes they won't. I always want exact answers, but it's okay. Like,
Okay.
and in every case, I noticed this. In every case, you didn't just skip it and do it. Like, you actually wrote down K equals, and you had the thing, and that was your saving grace right there. Like,
Okay.
you did that before then doing, okay, that's approximately whatever. Blah, blah, blah. And so,
Okay.
but I'm a big stickler about exact answers because I'm a math guy, not a physics or chemistry guy. So, but that's
Yeah.
me. Okay, that's my demon that I need to fight. All right. So, all right. So you tell me what to write. What am I doing here?
Um.
No, leave it alone.
Sit down.
No, leave it alone. Peter. Okay, so what am I plugging in and what am I getting out?
62. No, wait.
So look
I
at
don't know.
here. We did all the work earlier. All the work is right there. What am I plugging in and what am I getting out? Where's my input axis?
T.
And so this is, and I didn't write anything about it, but T is the big T is the thing that we're looking for. This is the age of the thing. Right? It's the amount of time. It's the amount of time that it's taken for our thing to go from its original amount until this bit, which is the amount of time that we're looking for. So that's the amount of time it took. So my input value is the thing I'm looking for. That's why I'm not just calling it little t. I'm saying it's a specific value, big T. That's why I made it capital. So what is my input? The input is this thing right here.
I thought I said that.
Oh, sorry. I probably couldn't hear you over.
Oh, okay. I was like, I said that earlier, and I was like,
I'm sorry.
no worries, no worries.
Okay. And so when that's the input, what is the output?
38 times P0.
Is it 38 or?
Well, is it a 0.38?
You tell me. You told me how to write this stuff up there.
0.38?
Why is it 0.38? What is 0.38 times P0? Why did we write that in the first place?
Because it's the remaining,
The remaining percent or the remaining fraction of the whole. Right?
yeah.
And so the question is that a 38 or a 0.38? You tell me. What did we do? How did we get it? Right? Like, well, we started with something, we took a proportion. Oh, it's got to be a 0.38 because, well, another way to do it. Look at how I've drawn it, right? That's a big number. That's a smaller number. If it were 38 times that number, it would be way up there. And so, but yeah, I'm just don't want to lose sight of how we got to where we got to and what all this stuff means. So, okay, I have an equation. There's two unknowns in there. One of them is P0, but oh, that's going to be nice. So then the only thing the thing that I don't have, big capital T, happens to be the thing that I want. And so now the name of the game is get big T by itself. How do we do that? It's the first step with this equation as I have it written.
Okay. 3 to that thing and then times T. So the first thing you do is, I believe, is to divide each side by P0.
Yep, I like that. And even if it didn't happen to be P0 on both sides, if this was like a 4 and that were a 5, that would still be my first step. Because I'm trying to get T by itself and I'm working my way out. I say the last thing that happens is this guy here. So we're going to get rid of whatever that is. Lo and behold, that happens to make our lives easier when I do that on the left-hand side. So that's cool. That guy goes away. We're left with 0.38 equals E to the natural log of 1/2 over 5730 times big capital T. Now what do I do?
I take the natural log of each side.
Yes.
Jesus.
Oh, no, you don't know cheese puffs, buddy. You've had too many. And that gives me whatever's in here.
Yeah. Pick it up. Pick it up. Tequila.
Easy, Kayla.
Hi, Peter.
You say hi?
Mwah.
Oh, that was sweet. Good kiss. All right, buddy.
Bye.
Bye-bye.
Bye.
So now what do I do?
Now you divide by, oh gosh, K.
Uh-huh. There's
You're
another
not-
way of doing that. What do we do to fractions? I have a denominator.
Oh,
I'd like to kill it. So I'm just going to kill it. Both sides by 5730. And I mean, if you didn't do it this way, it's perfectly fine. But that's usually how I do it. And then I say, okay, so I need to bring the thing in the denominator up into the numerator and bring the thing in the numerator down into the denominator. And so that gives me, I'm just going to go ahead and write it right here, 5730 natural log of 0.38 over natural log of 1/2 equals big T. Right there. Now you said divide by that. I'm going to do that real quick, just to drive a point home. If we had divided by that number, we would have natural log of 0.38 divided by this ugly thing, which is
yeah.
natural log 1/2. But all is not lost. We don't need to worry about this. It's just that regardless of how you go about doing this, if you could see, like in your mind's eye, what's about to happen. If you could see that this number is going to come into the denominator and give you something really ugly like this, you could then see like, well, dividing by a fraction is the same as multiplying by the reciprocal. And so this is the same thing as natural log of 0.38 times the reciprocal, 5730 over natural log of 1/2, which is exactly what we wrote, just a little bit differently, right? And so, I mean, any way you want to write this, when you go to act like this is perfectly fine, this is perfectly fine, that's perfectly fine, they all mean the same thing. And there's no right or wrong way to get to the right answer. Well, there are wrong ways, but I guess they're not, you wouldn't get to the right answer. Getting to the right answer, it's a right way. And so there's no wrong way of getting to the right answer. So, okay, let's figure out what this is. I'm going to get my calculator real quick. I'm not going to pull it up because this is an easy one to do. I'm just going to say what I'm doing here. So it's going to be 5730 times natural log, so times ln of 0.38. Take that and divide it by the natural log of 1/2 ln. I could go 0.5 or I could go 1/2. I'm going to go natural log 1/2 end parentheses. And we get, finally, oops, we get that T is approximately 7998 point, say 67. What's the units in that? Of that?
Whoa.
Yeah.
Years?
Years. It is years. Yeah, it has to be. A bunch of different ways we can think about that, but the way that we got all of this was we said, well, hold up. We measured this thing right here, the 5730. We measured that in years, right? We said that it took 5730 years to do this. We can make a bunch of different arguments to show that this has to have units of years too, but the idea is usually pretty simple. If you're working on a math problem and everything you've done thus far has been in years, your answer is going to be in years. And so we're going to say it's been this many years. Okay, now let's just kind of go back and think about if all of this makes sense. Because sometimes like you'll do the wrong thing, you'll solve for something, and you'll end up with, say, 0.38. And you go, okay, the time is 0.38. And if you stop and look at what you're doing, you go, wait, does this make any sense? First off, 1/2 of the original, 0.5 P0, by the time it took, well, its half-life to get there. Right? That's what half-life means. It's the amount of time for carbon-14 to decrease by 1/2. And so when we're at 0.5 times P0 or 1/2 times P0, then we know we are at 5730 years. Now I'm just looking at this and I'm going to see, well, yeah, T had better be on the right side of this in this graph because it's going to take longer for it to decay, not down to 50%, but down to 38% of its original value. So, okay, that agrees with that. That looks nice. And we could make more sophisticated arguments here, but I mean, we don't really need to. I feel good about this answer. Things look like they're coming out right. So there we go. That's it. It's a lot of work for one problem because we didn't have this little guy right here. Right? They didn't just tell you that K was equal to this. We had to go and find it. And it's not until like the very end where they say, see exercise 28, where you could find that, but it's not just given there either. You have to go and actually calculate it. So this is an involved problem. But these are really, really important to know. I don't want to just gloss over these. Like half-life, it's a carbon dating is a big deal, man. It's really cool. You're gonna see it a lot. So I'm gonna go into that. Okay, any questions? Do you feel good about this?
Yeah.
Okay, good. All right, so we're gonna talk briefly about a few things that are not in your book, but it's about the natural log and the exponential function. I'm going to start off with this. Is that how you spell every, or is it EVRY? It's EVERY, right? Every?
Yes.
Okay, thanks. Every exponential function is E in disguise. Now I'm going to have a real hard time with disguise. Disguise. What do I mean by that? We're not closing anything. There's nothing open. Sorry. So what do I mean by that? I mean that every exponential function, it's like the kinds that we've been talking about, right? Some base raised to a power can be written in terms of E. This is what I mean. And just, we're going to do this a couple different ways. Okay, this is what I mean by that. Let's say that we have an exponential function, and let's say it's 2 to the x, the first one that we ever taught. Okay, I claim that this function is just e in disguise. What I mean by that is that we can rewrite this thing as e raised to a power. And it's just some number times x. Now, the only thing that's left to determine is we just have to find which value of k makes this true. In other words, let's see if we could solve this equation for k. I'm going to let you work on that for a minute.
Would you take the natural log of both sides and then you get the natural log of 2 equal, or the natural log of 2 to the x equals the natural log of e to the kx, which is just kx.
Yes.
And then you can take the x out and you have x times the natural log of 2.
There you go.
Or what?
Yeah, x
No?
is the natural log of 2. That's what you said.
Oh, I thought you said no.
No, I said yeah, or I said
Oh.
go or something like that. Like, yeah, you go.
Okay, and then divide both sides by x.
Yes.
And then you get the natural log of 2 equals k.
There you go. Okay, natural log of 2 equals k. All right. Did we divide by 0? Because this is true. This will be true. So it will be true that 2 to the x does equal e to the kx, but I'm going to write k as log 2 times x, but I'm going to write my x on my left-hand side because that's what I do with logs, right? So yes, this is true. Problem is, whenever you do something to prove something or you're doing anything in math, you have to stop and say, wait a second, did I divide by 0? Because it might not be true if I divided by 0. Like, you might run into some problems. And so the question is this true when x equals 0? Well, let's just forget about everything you've done here. Forget about all that work. And just let's see what happens here when I plug in a 0 for x. 2 to the 0.
That, what? Yeah, that works, doesn't it?
2 to the 0 is 1. This is e to the 0 is a 1. And so it's already true when x is equal to 0, right? And that's going to be true for no matter what value of k you put there. This is every exponential function, well, like this, goes through the y-axis at 1. And so, yeah, that's always going to work. And so the only problem we may have had in this is when we divide it here, it's like, well, you can't divide by 0, so your result might not be true for every single value of x. But we've seen that, well, that's the only hang up there. And we've seen that, well, when you plug in a 0, it's already true. And so it doesn't matter what value of x you used. Even if it were 0, we could see that it would come out. And so my whole reason for doing that, normally we don't stop and think about those types of things, but it's good to know. But what I found is this is for all values of x, for all real values of x, this is true, no matter what. The function 2 to the x is equal to e to the natural log of 2 times x. Okay, and so now this is one way you could do this. In fact, let's do it again, but for a different function. Okay. Instead of 2 to the x, let's do something else. Let's do this. Five quarters to the x. You tell me. I want to know the final result. I want to know what the k value is. If you could write that value in there, k times x, find k. What do we get?
More.
Would it be the natural log of 5 quarters equals k?
I believe so. Let's double check that. I'm going to take the natural log of both sides. 5 quarters x equals, I'm not even going to bother doing it. I know when I take a natural log, it makes that stuff pop out. The x comes out by our favorite.
Yummy.
Oh, buddy, you can't have any more cheese puffs. You had a lot of them now, like way more than I wanted you to have. So then we divide by x and go, oh no, we can't divide by 0. That might taint all of our results. What if we just divided by 0? Well, what if you did? If it's a 0 and a 0, you're still good. Okay, so this should work for everything. K should be that, just like you told me. And so we could rewrite this as natural log of 5 quarters times x. I could put the x on either side, but there you go. Right? So this seems kind of trivial at first, but this will become your best friend in other math courses you take. If you could take a function that's something raised to a variable power and rewrite it as e raised to k times a variable power, then your life has just been made so much easier. And this is one I find that people just forget all the time. Now, there's another way of doing this though. And this is, so I'm going to leave this up here, but let's do something else. Something slightly different. 2 questions. That's log of e to the 4.5 equals what?
Um, 4.5.
4.5. Trick question. You weren't supposed to use your brain for that. Okay. Here's another one. Here's another one. E to the natural log of, how about 21.3 equals what?
Hmm. $21.3.
1.3, right? Whatever goes in, we've done something. We took the log of something, and then we undid it by taking that value, e to that value. It just undoes that thing. And so if I said, okay, what if I plugged in a 7? What would the output be?
$7.
7, yeah, okay. So what you're saying is whatever I plug into here is what pops out here, yes?
Yeah.
Okay, so if I, for instance, plugged in a 2 to the x, then the output would be a 2 to the x, right?
Yes.
Yeah, and so what you just said was 2 to the x is equal to e to the log of 2 to the x. How can we simplify this a little bit? Make it look like something we just saw on the board?
E to the x times the natural log of 2.
And look at that. We get the same thing we got before. The problem though, so we're going to do this one more time. Actually, we're going to do this one more time. So this comes from the fact that these things are inverses of each other. No matter what I throw up there, it pops out here. And so I could say, well, then 2 to the x is equal to e to the log of 2 to the x. 5 is equal to e to the log of 5. 7 is equal to e to the log of 7. And so when you have an expression like this with something in the variable, we could use our favorite property of logs to pull that value out and rewrite this guy in a way that it may not seem like it now, but this way will help you so much in your life, so much that I'm devoting an entire like half of a class to it. But this thing, I cannot stress how important this little trick is to you. That you could say, well, if I have any number, 5, I could write that as e to the log of 5. If I have 5 to the x, that's e to the log of 5 to the x, which makes my life easy if I can rewrite it like that. It'll be your best friend. The only problem with this is what values can I not plug into log? Right? Because we have a restriction on the domain of log. I can't just plug in any old number. Natural log of some value, whatever goes in there. We must have what's the problem? We can't plug in what's?
0.
You cannot plug in 0. What else?
The negative numbers.
Negative numbers. We cannot have them be 0 or a negative number. In other words, x has to be bigger than 0. Now, and I've said before, it's true that you can plug in.
1 second. Okay, sorry about that.
Hey, no problem. And the idea, though, behind that, the reason why is that the function e to the x has only positive outputs, right? That e to the x is always going to be a positive number, no matter what, right? And that's the same with like 2 to the x or anything like that. And therefore, to ask the question log of something, log means you took a number, plugged it into e, and got some output out. You got some y value. And then you said, okay, well, I'm going to take that and pull it back and see where it came from. That's what that means. That's the natural log of that number. And so all of those numbers that go into the log function have to be positive numbers. Otherwise, what we're saying doesn't make sense. And so when you go to apply this trick, what I'm getting at is that this trick's always going to work just as long as what goes in there is a positive number. Like I said, 7 equals e to the natural log of 7. Oops, sorry, buddy. But it's not the case that we could just easily say negative 3 equals e to the natural log of negative 3. Because as far as we're concerned, the natural log cannot handle negative inputs. And so we can't just do this willy-nilly without using our brains. We have to stop and use our brains sometimes. And when, and like, that's kind of the payoff we get for not having to solve that equation, right? Like the idea was I could take something 2 to the x and write it as 2 to the x equals e to the kx and then do some stuff. Or we could remember this nifty little fact that I just say, well, 2 to the x is the same thing as e to the log of 2 to the x. And that's great. You could just jump right to that as long as we remember that you cannot just willy-nilly throw in a negative number into log. And so here's another interesting thing is, do we have a problem with that here? Is 2 to the x ever a negative number?
No.
No, it's not. And just to be perfectly clear about that, I'm going to say, well, let's just look at 2 to the x. This is 2 to the x, goes through here at 1, right? It's always positive that way. It's always positive that way. We never have to worry about 0. We never have to worry about a negative number. And so for every value of x, we could just do that. It's perfectly fine because 2 to the x, this thing will be a positive number, always. And so we don't need to worry about it. And so it's not a book. I'm sorry. Okay. So last little bit here is just to say so we went to derive that by solving an equation, but we could also say that some number raised to the x equals what to the what of what?
I'm sorry.
So let's do our trick with this number here. This is the same thing as what?
E to the x.
Well, yeah, but let's not skip ahead. Let's say that we hadn't seen this before. This would be what?
So the natural log of 5/4 to the x.
Yep. And then we do our favorite thing with log, and that's what?
E to the x natural log
There you go.
of 5/4.
There you go. Which is what we got by solving it with an equation and stuff like that. But then the only thing we would need to go back and check is, wait a second, is my input to log always positive? And yeah, 5/4 to the x is always a positive number, no matter what. Even if it were 4/5, even if it were a decay, right? Or if it were like 1/2 to the x, and we know it's getting smaller and smaller, it's always going to be positive, and so we're always good to do it. And so, long story short, here's the takeaway from this. We got like a minute left. Is any number you have raised to the x, we could easily just say, well, that's the same thing as e to the log of a to the x. We stop and go, wait, can I plug in a to the x into log? Yeah, I can plug a because a to the x is always a positive number. So we're good to go. And so finally, that x drops down. And we see that every exponential function is just e in disguise. This little principle right here will help you so much in your life.